Io mi presento, appunto, sono Elisa Mosconi, mi occupo di divulgazione scientifica e di missione per la Fondazione Aviano Medicina da anni, sono responsabile di AIRC Campus, che è il progetto a cui state partecipando. Il logo di AIRC è piuttosto noto, vediamo se va avanti. Eccolo. Di solito il nome anche, però non tutti hanno chiaro di che cosa si occupi. Fondazione, da allora l'obiettivo è sempre stato solo uno, ossia rendere il cancro sempre più curabile. Cerchiamo di perseguire questa strada fondamentalmente attraverso due canali, prima di tutto finanziando la migliore ricerca oncologica in Italia. Considerate che ogni anno nel nostro paese lavorano più di 5.000 ricercatori grazie ai finanziamenti di AIRC. Oggi abbiamo, come dire, un sottogruppo di rappresentanti. Tra l'altro questi fondi derivano solo da donazioni di privati, quindi è un grandissimo sforzo collettivo italiano a sostegno della ricerca. E parallelamente cerchiamo di fare corretta informazione scientifica, corretta divulgazione. Giusto per darvi un numero, vi posso dire che nel 2021 abbiamo destinato alla ricerca sul cancro più di 136 milioni di euro, che sono diventati 741 progetti di ricerca per ricercatori affermati, 93 borse di studio per giovani ricercatori, quindi un domani anche voi potreste essere borsisti AIRC, e 22 programmi speciali. Vi dicevo, la comunicazione è parte della missione. Perché è importante comunicare? Prima di tutto perché è importante dare ai donatori la finalizzazione del loro contributo, quindi è importante dire alle persone, detta in maniera molto semplice, dove sono finiti i loro soldi, quindi riportare a chi ci sostiene i risultati che sono emersi nei laboratori. Ma parallelamente è importante mettere le persone nelle condizioni di fare delle scelte corrette per la propria salute, quindi informarle su cosa possono fare, su come si dovrebbero comportare per proteggersi. Quindi cerchiamo di comunicare tanto, di farlo bene, parliamo a tanti pubblici diversi attraverso diversi canali. Qui ci sono un po' di esempi, c'è quello forse un po' più noto perché ci sono le case dei vostri nonni, si chiama Fondamentale Nostro Organ, arriva alle case degli italiani appunto in milioni di copie. C'è un sito molto visitato che è AIRC. Approfitto per invitarvi a seguirci sui social, noi abbiamo 2 account Instagram, non uno, non ci facciamo mancare niente. Uno istituzionale che è AIRC, che parla in maniera un po' più specifica di oncologia, chiaramente con dei toni e con dei format adatti al mezzo, e poi ce n'è un altro relativamente nuovo che si chiama wonderwhy.it, con dei format innovativi, collaborano con noi dei divulgatori scientifici, ci sono dei reel, quindi insomma cerchiamo di essere i più attuali possibili. Con questo secondo canale non parliamo solo di oncologia ma anche di scienza in maniera allargata, quindi insomma seguiteci. Ci sono poi tante attività con i media esterni, con le scuole, con i festival della scienza e poi qualche anno fa il campus. Il campus è nato proprio a Padova nel 2016. Quando l'abbiamo presentato al rettore di allora ci ha guardato e mi ha detto: questi sono matti, cosa vogliono? Quindi è stato un grande esperimento per Fondazione AIRC ma anche per l'università. L'obiettivo qual è? Condividere con gli studenti, quindi con voi, i nostri contenuti. Chiaramente AIRC si occupa soprattutto di ricerca sul cancro, quindi lezioni come quella di oggi sono il cuore del contributo che noi possiamo dare, speriamo quantomeno, alla vostra formazione. In realtà è una realtà molto grande che appunto comincia ad avere una storia e una serie di esperienze anche in altri campi, dalla comunicazione appunto alla gestione del personale, alla parte economica, quindi sono tutte esperienze che possono essere spese in contesti diversi. Facevo prima un esempio vostro professore, io tra un paio di ore sarò a psicologia del lavoro e ci sarà la collega che gestisce i volontari di AIRC a portare la propria esperienza ai ragazzi che un domani potrebbero fare il suo lavoro. Le persone sono sicuramente la forza di AIRC. Vi dicevo, sono più di 5.000 ricercatori che lavorano grazie a contributi della Fondazione, ci sono 4 milioni e mezzo di sostenitori che sostengono appunto la ricerca a vario titolo, con donazioni di vario tipo, 150 dipendenti che lavorano per la Fondazione, tra cui anch'io chiaramente, e 20.000 volontari. Questi volontari sono quelli che vedete nelle piazze quando ci sono le grandi iniziative di raccolta fondi, la zalea della ricerca in occasione della festa della mamma, ci sono i banchetti, distribuiamo le azalee, le arance della salute, i cioccolatini un paio di settimane fa e poi una serie di altre iniziative più piccole sul territorio. Quindi quando vedete queste persone ai banchetti sappiate che sono lì totalmente a titolo volontario, quindi lo fanno per dare un proprio contributo personale alla ricerca sul cancro. 20.000 volontari sono tanti, quindi rispetto ad altre realtà associative siamo sicuramente molto fortunati, ma in realtà c'è gran bisogno di cambio generazionale. Quindi io approfitto per invitarvi a diventare volontari di AIRC. La ragazza che vedete non è una modella, quindi non è una finta, è realmente una volontaria, vedete che è giovane, quindi insomma è una cosa che si può fare. Non serve una preparazione specifica, ci si può impegnare anche solo una giornata all'anno, le possibilità sono diverse, poi lascio sicuramente ai professori le slide con i riferimenti, quindi insomma ci sono una serie di iniziative sul territorio in Veneto a cui potete partecipare. C'è una pagina di riferimento che è generazioneelect.it, io poi chiaramente resto a disposizione a fine della lezione per delle domande molto volentieri. AIRC è una realtà nazionale, però ha 17 comitati regionali che sono fondamentali per il rapporto con il territorio. Quello Veneto ha sede a Verona, questi sono i contatti dei miei colleghi che sarebbero molto felici di accoglierli nella loro squadra. Ho terminato, vi ringrazio, lascio la parola al dottor Baldassarre.
Let me just introduce Dr. Gustavo Baldassarre. He is a medical doctor who is also the head of the molecular oncology and preclinical models of tumor progression at the Comprehensive Cancer Center of Aviano, Pordenone, Italy. He also leads a laboratory in charge of molecular diagnostics of solid tumors in the same cancer center, and the laboratory on the control systems of invasion and cell growth at the CRO of Aviano. He obtained his medical degree at the Federico II University in Naples, and then had a postdoc experience at the Fondazione Pascale in Naples and the Sidney Kimmel Cancer Center of Philadelphia. He started working at CRO in Aviano in 2002, and he established his own group there. So he's an expert in ovarian cancer and the DNA repair mechanisms, as well as resistance mechanisms to platinum compounds, which are widely used to treat this cancer type. And so I'm very pleased that Gustavo accepted our invitation to come to Padova and deliver the lecture. You can, of course, work, just maybe take care of be around this object, because you are being recorded.
As mentioned by Stefano, everyone, we can have a lesson which you can stop me. That's something that you want to be better clarified. And this is the part that usually who, like me, like Stefano, do research after medicine school, usually does an experience abroad and then a lab in Italy. And I want to let you know that almost all of us that do cancer research somehow in their career have the support of AIRC that is still very important. So why we do cancer research? I think that the main reason, at least for me, is that when you do research, you can impact on the life of person, not just in this moment, but in the future. So if you understand why any disease develops and how this disease develops, you can really impact on the survival and the benefit of many people. And this is how I prepare this presentation, trying to demonstrate you that the research along the years lead to better cure and treatment in ovarian cancer, at least some of them. Research, as mentioned before, is not for now a single individual, but for many people in the future. And but why cancer research? Because cancer is a disease that we can now treat much better than some years before, but still need more research to understand better the mechanism, to understand better the molecular alteration in the tumor and in the whole organism, and try to provide more personalized treatment. Which type of research are important? All types of research are important. Of course, we have basic research that goes into the mechanism of the disease, the molecular mechanism inside the cells. We have clinical research that is more related to treatment of patients with some drugs and comparing different types of treatment. We have population-based research that go wide to understand which are the environmental factors that could impact on any disease. But what we do is translational research, that is the link between basic research and clinical research. Try to move from molecular basis of mechanism to the treatment of patients. And in fact, we can say that translational research is from bench to bedside. So we have an idea, and then we try to verify if this idea is worthwhile for the patients, or we can, starting from a specific problem that may have, unsolved problem that may have the patients, and go to the bench, understand how the problem is based on, and then go back to the patients. And of course, when we do research, we refer to the cell. The cell is very complicated. I do know that you have already done biology classes, and so you already know that cells is very, very complicated. And also you should know that since we are not so smart, we have to simplify the cells and try to focus on some specific intracellular alteration or model alteration to try to understand the complexity. So we almost always refer to oversimplification of what's really happen in a normal or a transformed cell. Cancer is a genetic disease. This is the first phrase that one of my mentors already started his talk. And anyway, it's not one disease. There are more than 200 diseases, different causes, different organs, different gene alterations. So there is a wide heterogeneity, but almost all the cancer has some hallmarks. This is the first attempt from scientists to put together which are the complex alterations common to different cancers. And as you can see that these are the ability to proliferate, so cancer cells do not stop their growing, the ability to do not die in the presence of external factors that could lead to cell death for normal cell, the ability to invade, the ability to be mortal, so the unlimited potential of replication, the ability to form the vasculature that could feed the tumor that is necessary for a tumor to grow over specific sites, and of course the ability to resist other mechanisms of death. This is 2000. 10 years later, we do know that the situation is much more complicated, and the hallmark of cancer should be taken in present that there are also the interaction between cancer cell and the host, so the ability of the host to respond to the presence of cancer cell and activate immune response or other type of alteration. But the good news that the research for each of these hallmarks identify possible treatment that could represent for the different type of tumor specific ability. So going on with the research, we can of course ameliorate the treatment by understanding the underlying mechanism. And to do this complex job at the beginning, 10 years ago, when I started to work in ovarian cancer, we used cell line, very few cell line. Now we have established cell line in the lab, but since the complexity of the disease is very, very high, we should also rely on a different type of patient-derived models like organoids that are grown from specific piece of tumors and resembling in vitro the ability of this specific tumors of that patient to grow and proliferate in a three-dimensional matrix. Also, we should use animal models, and this is important. There is a little bit of fight in Italy, but also abroad, between the animalists and the people that do research, but the use of animal model is absolutely necessary, because at least for me, I would not be the one that would test a new treatment, a new diagnostic procedure that has not been proven in a specific animal model. If, of course, to do research that on animal models, there is a very, very complex protocol that you should present to the Ministry of Health, that should be approved for the scientific validity, and should be guaranteed the Ministry of Health that animals are treated in the best way possible without suffering. So for us, a little bit more difficult to do clinical trial with mice than with humans, because mice are more right than humans, also because they cannot stay. We should be sure that they do not suffer so much. In the mouse model, we have the genetically modified mice, which that we can modify the genome of the mice to lead to the tumor formation or tumor prevention. We can use patient-derived models that, like organoids, it's a piece of tumor from the patient that grows in the mice, and we can imagine how to treat these specific tumors, and then we can have more simple models. These models are necessary to do translational research that, in my opinion, should focus on what is necessary to understand for a specific disease in that is not still clarified, and so it's a problem for the patients. And this should be a circle that then always return to the patients, trying to resolve this unmet clinical need. So, two words about ovarian cancer. Ovarian cancer is a quite rare disease. It's not very common. This is the frequency of tumors in women in Italy, and you can see that ovarian cancer is about 13,000–14,000 cancer in Italy, but it's quite deadly because it is the 7th case of death for ovarian cancer, and the number are quite high because we have about 3,000 deaths for ovarian cancer per year. The incidence of ovarian cancer is slightly decreased, especially in the younger people, but the mortality is not decreasing, because this decrease is dependent on the decrease of incidence, but the type of survival is almost the same since the last 40 years. So this means that some people with ovarian cancer can be cured, but most of them need better treatment and better approaches. And to do this, to do translational research, it is necessary to do work in multidisciplinary group. And we created this type of multidisciplinary group in Aviano in 2009. In this group, we meet together different expertise that from the surgeons, gynecological surgeons that treat surgically the patients, to medical oncologists, to research And as you can see, these are the different units that in CRO of Aviano work in this type of multidisciplinary group. We have medical oncology, gynecologist, radiotherapist, oncologist, and then research unit, different research unit, and then few aspects that are really important for the study of human cancer, that is the unit of pathology that collect the tumors and do the morphological diagnosis, and the biobank that store the tumors or any other sample from the patients that could be then analyzed to understand if the research hypotheses are correct. So why ovarian cancer are deadly? I list which are the my idea of the problem present in ovarian cancer research and treatment. First of all, the heterogeneity of the tumor, then the mechanism of discrimination, the fact that still ovarian cancer has a late diagnosis, and then the different response to chemotherapy that is my more specific field of research. So I will go through this aspect and try to show you which are the molecular basis of each one of these characteristics of ovarian cancer, starting from the high pathological and molecular heterogeneity. Again, if you want to interrupt me because I think that you not understand or I did not explain well, you can anytime, no problem. This is what we think some years ago was the origin of ovarian cancer. We thought that ovarian cancer, the ovary as a line of epithelium. Of course, I'm talking to you just to epithelial ovarian cancer that are the most common type of ovarian cancer. Then we have cancer from not the epithelium, but the cell of reproduction, so the germinomas and so on that are not the topic of my treatment, also because they are not, even more rare and almost always curable. So we focus on just the epithelial ovarian cancer. And this epithelial ovarian cancer should, we thought, start from the transformation of the ovary epithelium, not the internal cell of the folliculum, and could then differentiate in different histotypes. After years of research, we came out with this new paradigm in which ovarian cancer can be divided in two types based on the grade of the tumor, so how much the cells are differentiated or not, and the type of differentiation and the origin that is not only from the line of the ovary, but also from the fallopian tube or maybe from the other organs that then give to rise different morphological type of tumors that could anyway, based on their molecular characteristics and behavior, divided in two big groups, type 1 and type 2. And this division is important for us trying to categorize better patients that could respond to different type of treatment. How we reach this new classification? This was mainly due to the fact that at least 20–25% of patients with ovarian cancer develop ovarian cancer for the presence of a mutation in some genes in the family, so a familial ovarian cancer. The gene of the strong candidate of genes responsible for the desired onset of ovarian cancer was cloned in 1994. I think none of you were born that day, but this was a major breakthrough for breast and ovarian cancer research, because we now know that about 80% of familial ovarian cancer are due to the mutation of BRCA1 or BRCA2 genes. They give different predisposition to develop ovarian cancer. Maybe mutation in BRCA1 is more keen to give ovarian cancer respect to mutation in BRCA2, and also the prognosis of the two groups of patients are quite different. This is the tree how familial ovarian cancer manifests itself in a family. I choose a very famous family history, that is the Angelina Jolie story, in which you see that both the grandmother and the mother of Angelina and the sister had ovarian cancer, and so you can see that this is a typical history of genetic transmission disease. Then we have some other genes that could lead to ovarian cancer, although not so specific. In particular, TP53 mutation causes a syndrome that is called lymphomania, that is definitely positioned to different type of tumor, and the Lynch syndrome also could give rise to ovarian cancer, but also any some other type of tumors. There are still not identified genes, and there are genes that are involved in the pathway of DNA repair that is called homologous recombination, which we will talk about later. So, why it is important for the morphology of the tumor? Because by analyzing the fallopian tube of patients that were operated to remove ovarian tubes to prevent the onset of ovarian cancer, or were operated because of the possibility to develop ovarian cancer because they were BRCA mutated, pathologists identified the presence of this line of transformed cells that are positive for TP53. It means that this TP53 is mutated. And this is the first left lesion that we can identify in the development of ovarian cancer, that was called TIP, that means tubal intraepithelial carcinoma, that is characterized by still low proliferation, but the presence of DNA damage and the presence of mutation of it. And this is the first cancerous lesion that we can find in the BRCA1 and 2 patients. And so we think that at least a portion of ovarian cancer originated from the tumor. So, looking at this new type of calcification, we can say that there is specific signature and mutation in the fibria, but also could be presence of different different type of alteration on the ovary, and this could be the start of ovarian cancer. And depending on the type of ovarian cancer, we have different molecular alteration. I told you about the fallopian tube origin that is due to the mutation of BRCA1, 2, and TP53 as main driver mutation. Then we can have ovarian cancer that are based on mutation on other signaling pathway, like the RAS PI3 kinase pathway, or we can have mutation based on the mutation of other gene like mismatch repair pathway or identification. And this gives to different type of transformation and different type of tumors. So the molecular basis of the tumor are really important to determine how the tumor manifests itself. This is more or less the same in the same description in put as a table in which we can now group based on the morphology and the mutation the two types of ovarian cancer. So we have type 1 ovarian cancer that are low grade, that are of mainly endometrioid, mucinous, and clear cell carcinoma based on the transformation of receptor signaling pathway. So all the genes that can be activated by normally in the cell by the stimulation of the cell with growth factors. So the KRAS genes, the beta-catenin, beta-catenin pathway are all related to type 1 cancer. Instead, type 2 cancer are related to mutation of p53 and PSCA1 and 2 genes. And this different type of mutation make also the genome of these tumors completely different, because while type 1 serous ovarian cancer has a normal genome chromosomally stable, type 2 ovarian cancer, because of this mutation in the DNA pathway and with the presence of mutation, are usually present with different widespread alteration of combinant variation, that some chromosomes are overrepresented and some others are underrepresented. And this is a typical characteristic of type 2 ovarian cancer that unfortunately are the most common type of ovarian cancer. So this is, you can see already that we have a very big heterogeneity. Ovarian cancer is not a single disease, it's at least 4 different diseases with different morphology, different mutation, different type of evolution and origin. But this ovarian cancer also has a way to disseminate that is very peculiar. It's very peculiar because it is located in the abdomen, and it forms from the tube, and then from the tube that it can spread not just through the hepatic vessel or the lymphatic vessels, but also directly into the abdomen. This is how appears a patient with ovarian cancer, with all these small lesions are tumor, and so the ability of the surgeon to remove all these tumors should be very high.
Describe obviously time oncology. Why isn't it as significant for
Then oncogene is present in some type of ovarian cancer, because in this type of tumor is more mutated. But when you say you see the kinase pathway alteration, it almost always means that P10 could be altered, because P10 is a negative regulator of the cancer. So somehow, sometimes to simplify the thing, we refer to mutation of the pathway rather than to the whole gene. But you can see P10 here is present in low grade and in clear cell carcinoma. And so for the type 1 ovarian cancer, it's quite different. Actually, and so surgeon is the most, maybe the most important physician in the treatment of ovarian cancer, because we know that if he can remove all the metastatic and primary lesions, the survival of the patient is for sure wrong. This is the first prognostic index, the ability of the surgeon or the possibility of the surgeon to remove all the visible masses and reach what they call R0, so zero residual of tumors. And anyway, this lesion born from the ovary epithelium or from the fibula, and then detach, and then can be transported in the fluid circulation that is normally present in the arm. And so they can flow through the abdomen and pelvis. And then when they found the epithelium or that cover the abdominal organ or the peritoneum, they have the possibility to attach and regrow. So they detach as a spheroid and regrow as a bigger spheroid. And this process of dissemination goes on for years. And so usually we identify an ovarian cancer patient when the situation is like this one. We can, of course, study this type of dissemination, and we should have to understand how this dissemination occurs and how we can prevent it. These are models that we use in the lab to study dissemination. We use in vitro models in which we understand which are the genes important to allow the cells to attach to the mesothelium. So in red you see cancer cell, in red in green see the cancer cell, in red see the mesothelium, and you can see that there are some cells that can attach very well, and we can prevent their ability to lie on the mesothelium, and so this could be important to prevent metastasis. Or we can use the ability of spheroid to attach, grow, and invade the mesothelium. This is a mesothelium clearance called as experiment, in which in time lapse we can follow how a spheroid of ovarian cancer can attach and clear the mesothelium. This means that this spheroid here is able to break the matrix and the cell layer on which it is attached on. And then, of course, we have in vivo model in which we can identify these spheroids that can be isolated because they are floating around and can be analyzed. So in this manner, with the right model, we can understand the molecular basis of this dissemination. I will not go through this because maybe a little bit too deep. Then we have late diagnosis, and this is a problem. This is a big problem because you can see that if we have an ovarian cancer, any type, in stage 1 or 2, it is almost curable in 90% of the cases. And most of them, of these patients, especially for stage 1, do not need any other therapy than surgery. So if we have an ovarian cancer in early stage, we can save life. If we have an ovarian cancer in late stage, stage 3 and 4, this is how in oncology we stage ovarian cancer. So stage 1 is limited to the ovary, and the stage 3, stage 4 is the metastatic, and then we have a different distribution based on which organs are present of ovarian cancer cells. Anyway, in stage 3 and 4, we have a very bad prognosis for all the histotypes, both type 1, type 2, multiple. So the first thing we should do is try to have an early diagnosis. And in fact, if you look at the mortality, the number of patient diagnoses in stage distribution, you can see that the serous ovarian cancer, that is the most common type of ovarian cancer, usually diagnosed in stage 3 and 4, and the survival of the patients in stage 3 and 4 is very low. Why we do have late diagnosis? We have late diagnosis because we have very common and outspecific symptoms only late when the disease is very spread. This is some information prepared for the patients, and then as you can see, all these symptoms, some symptoms of the daily time, any of us could have had once in his life, and it does not mean that we have a cancer, but just that we could have some other type of problem. So mostly it's an underestimation symptom, and so it's very difficult to have an early diagnosis. And so what we can say to a patient is that in the presence of this symptom that may have been persistent for many times, you should then go to the doctor and see if it is something that you should, some exam that you should do more specific. But you see that also the timing of the advice is very big, because they say you have to have this symptom at risk for 12 months, so it is a very long period of time. And so the symptomatology do not help in the diagnosis, but also, since ovarian cancer is a medical problem and early diagnosis to save life, it has been tested the possibility to do screening in the general population to identify early ovarian cancer and verify if this approach could save life. Now, this effort was done mainly in UK with this big program in which they tested 200,000 women, either not screened, just recorded, or screened with a blood test that looked to the presence of a protein that is produced by ovarian cancer. It is very high in the, could be very high in the symptom of patient with ovarian cancer at late stage, not at early stage. So this is quite a problem. And or they could also have a ultrasound to see if or ear ultrasound and the blood test, so 3 groups. And they say after 12 years, I think this was after 12 years, okay, maybe we can save for life, or we do not. And then the last update that was from last year demonstrated that unfortunately this approach was not effective, because we can have no difference between groups. These are the number of patients with death or ovarian cancer. And you can see that the ultrasound group is here, the group not tested is here, and so it's very, very similar. So in this approach is not effective, it's also not sustainable, because you have also ARMS by a screen. The ARMS is mostly anxiety, because you live with the possibility that you have a diagnosis of ovarian cancer, but then it's not true. You could have unnecessary surgery, because it is maybe present, but then you have the operation and it was not ovarian cancer. So the way of seeing at least ovarian cancer is not now considered an option. We should think something different, go in this direction.
So this is an important issue of prevention. The screening was on general women population, not specific groups. like PRCA mutated patients, general population. For the our indications for specific groups with a genetic risk of ovarian cancer, of course, right? Yes, ovarian cancer. Not in a plastic patient with BRCA1 mutation should do instead screening. That should be tested yearly for the presence of ovarian cancer and of breast cancer, and at some point in their life could be offered the possibility of ovarian hysterectomy to prevent the onset of the cancer. But for this high-risk patient group, it is highly and strongly recommended to have a yearly transition.
At one point in the ovarian neoplasm, first sign of ovarian. At one point in the ovarian neoplasm, that's the issue. The mental cake and the first sign.
I don't think we have an answer, a precise answer. We can understand well is how many years are necessary for incremental localization. We do not have a clear question, a clear answer. I think that we can think that ovarian cancer spreading could be something that happens over maybe, but we are not sure that it is the ovarian cancer that could really spread and grow, because even in this case they could be very different with different diseases and different ability to spread and grow. So I think that the situation will show you with this big and disseminated growth may need time, but not sure.
Second question, I'm not a student, but very curious to ask. In the slide, there is a group 2 yearly blood test, and I think that was the CA1 biomarker. Now, you have shown before that it's a genetic early marker of this, or a part of this type 2 cancer, ovarian cancer. They have different mutations and accumulation of the protein. Now there are these new liquid biopsy tests that potentially enable us to detect mutations also in the blood sample. Do you think that in the future would be worth setting up such an expensive campaign by replacing the old blood test, so the CA1 to 5, with maybe genetic assay, like PP53 dosage blood?
Yes. Yes, this type of trial is done and has been done widely. I mean, not only for ovarian cancer, the work I'm thinking afterwards of what from my policy that was published in Science 10 years ago, and they define a senior modification coupled with also the presence of circulating biomarker like CA125 and others, the CA. And they find that in this way they are able to identify ovarian cancer, specifically ovarian cancer, with a specificity of 95% and a sensitivity of 90%. So this way maybe is the way. I'm not sure we are already there, and I'm not sure that there will be the possibility to do again this type of study that is really costly, because recording for 20 years, almost 20 years, I think this is 18 years follow-up, 200,000 women, not so easy. And also, we do not know if in early stages you identify already the presence of mutation. I mean, circulating tumor DNA is for sure present in late stage cancer, not sure in early stages. So maybe we can do a small trial with an aside. Then the response to therapy, I say that all these tumors at the end are treated with one therapy. This therapy is the association of two chemotherapy, that is a platinum compound, in this case is carboplatin, and a taxane, that in this case is taxol. So this is the most effective combination we can use to prevent the recurrence of ovarian cancer and try to treat patients. And this is so important, the response to this therapy, that our clinical colleagues divide ovarian cancer depending on how the patient responded to the therapy. So it means that if a patient recurs under the treatment, so the tumor starts regrowing during the treatment or when the treatment, it is a refractory tumor to platinum. It recurs within 6 months from the end of the therapy, it is a platinum resistant. This is a quite unique type of tumor. Then, if instead the patient recurs after 6 months or more, this is the group of platinum resistant. Fortunately, this is the large part of patients respond to tumors, to platinum, and we will see in a few moments why. But the unfortunate thing is that this tumor will become resistant at some point. So this is the quite biggest problem in my opinion of ovarian cancer. What we know that by the clinical trial is that, I said, carboplatin is extremely active in ovarian cancer. No other treatment are superior. Recurrent ovarian cancer become resistant, and we do not have a real need to platinum-resistant ovarian cancer, so we need translational therapy. To understand why patients become resistant or sensitive to platinum, we should know how platinum works. So platinum is an alkylating agent that binds the DNA and forms some lesion on the DNA that it can be repaired the cell survive, it cannot be repaired the cell dies. This lesion could be either a single strand lesion or inter-strand break, so different type of lesion. So this is why on the DNA, this is why platinum is so active in cancer cells that are highly fighting cells. But to reach the target, that is the DNA, the platinum should enter into the cell. Then, and this entrance could be either a passive entrance that is not very efficacious, or could be a active transport, and then once it is in the cell, it could be by enzyme like degli, or could be expelled, and then once in the cytoplasm, it goes into the nucleus, and also here should be transported to the nuclear pore, and then only then it bind the DNA and cause the DNA damage. Once the DNA damage is formed, the cell activated a linear transduction cascade that leads to cell cycle arrest that is necessary for DNA repair, that then if is not complete, lead to cell death. If it is complete, leads to cell survival. This is the general mechanism of action of platinum. And so, thinking to how platinum works in the cell, you can think which are the mechanism of resistance or sensitivity. For instance, if you think to on target effect, so the activity specific for which platinum is given to a cell, to a patient that is to DNA damage, you can understand that if your cell is able to better repair DNA, it can be resistant to platinum. If it is less able to repair DNA, more sensitive to platinum. And then we can have a different type of mechanism on the ability to uptake and expel platinum and so on, but I will go to this rapidly. I don't know if I'm talking about it. So on. So, if we think to the transport, we can have the increasing ability of the cell to expel the platinum, or the decreasing ability to import the platinum, and so this can be mechanism of disease. Also, the ability of detoxification, it could be a mechanism of resistance. But the most important mechanism of resistance or sensitivity to platinum is the ability to repair DNA, and in particular to repair this type of damage that is double-stranded. Also, platinum induces inter-strand cross-link and intra-strand cross-link that then at the end cause the doubles. The break of the double strand of the DNA, and this then activates a specific signaling pathway that is called homologous recombination, or non-enjoyed, but non-homologous enjoyed, but more rare. So, since ovarian cancer are usually detected in this pathway repair, you can understand that this could be the main reason why we are more sensitive to the target. Also, we can have a post-target effect due to the inhibition of TDP that in the type 2 type of ovarian cancer present in 99% of the cases, and this leads to evasion of apoptosis. And then we can have off-target effects that are completely unrelated processes by which a cell can survive a toxic treatment, that is, for instance, regulation of autophagy, proliferation, host generation, etc. And these are all means by which a cell can survive in the presence of a cytotoxic drug. I would spend a few words on the DNA pathway, because since 2011, when ovarian cancer were deeply sequenced by the consortium of Cancer Genome Atlas, we do know that 50% of the ovarian cancer patients are mutated in the homologous recombination pattern for DNA repair. That means that not only are mutated for BRCA1/2 or methylated for BRCA1, that means that the BRCA1 is present and not mutated but not expressed, and so it's like it is absent or mutated, but maybe also altered in other genes belonging to the same pathway. And this means that on one side, the BRCA mutated patient has a better prognosis because they better respond to the therapy, but also that there is at least 50–60% of patients that are deficient in this pathway of or could be deficient in this pathway and could benefit from platinum treatment. This is just another example that BRCA mutated patients in the past year responded better to chemotherapy. And this is a concept that I would like to bring to your attention, that was developed in the early 2000 by a visionary scientist that is called Alan Ashworth, that started to think that since DNA repair could be repaired, DNA damage could be repaired by different pathways, homologous recombination for some type of damage, but also base excision repair for single cell rand, mismatch repair for mismatching damage, and so on. It started thinking that if a cell could repair damage by homologous recombination is altered, maybe it can be saved by another DNA repair pathway. But that if the homologous recombination pathway is altered, for instance, because SCI1 and 2 genes are knocked down or mutated, it could be linked to the presence. It could be important to block at the other pathway, and this could lead to genomic alteration not reversible. And this is what he proved with a seminal work in 2005, which he crossed mice knockout for BRCA1 and mouse knockout for PARC1, and so that these cells do not live because PARC1 is involved in the repair of base excision repair, of the damage of a single strand filament, and the concomitant abrogation of this pathway by deleting or blocking this gene, and this pathway by deleting or blocking any genes in the homologous recombination pathway, lead to irreversible cell death for altered genomic rearrangement. PARC1 is important because we now have PARC inhibitor. This is one of them. And the PARC1 is a protein that does some specific job, that is its varylation. So it adds sugar on its target protein, and this is a process that is dynamic. So each protein could be either parilated and deparylated, and the balance between the parilated and deparylated protein lead to the function of this protein, especially in the context of DNA repair. We do have enzymes that could block the active catalytic site of drugs that could block the active catalytic site of the enzyme, and this leads to the loss of parilated protein in the cells. This is a cartoon that explains the concept that I already explained of synthetic lethality. And if we use a PARP inhibitor in a cell that do not have homologous recombination, the cell could not switch between repair pathway. The protein, the PARP protein, remains entrapped in the stalled replication fault, and we have complex arrangement. And this treatment has been proven extremely active in cancer that are frequently altered in homologous recombination. These are the first study that was published in 2015 for ovarian cancer patient mutated for BRCA1 and 2, and you can see that adding PARP inhibitor to the platinum treatment after platinum treatment increase the survival of this patient, and this has been confirmed over the year. This is another inhibitor that do the same in the presence of BRCA1 and mutated, but also in the presence of homologous recombination alteration. And in fact, this is the way now, after 40 years, finally we change the treatment of ovarian cancer, just because of research, on how the cell responded to platinum, in which we saw that if we add two specific group of patients, so the one that respond to platinum sensitive patients, the PARP inhibitors, different type, we have 3 in the clinical trial, use darbepoetin, olaparib, we can prolong strongly the survival of the patients. So this is a major breakthrough in the treatment of ovarian cancer. Of course, we now are learning that there are resistance to this treatment and there are possible side effects that we should think long-term side effects we should think about it. And I can stop here because now should be a part in which I prepare to present you a specific project we did on this topic, but maybe you are tired and or you have a question, and so I